I'll do the plain biographical detail first. So he got a BS in physical engineering from the Technical University of Berlin in 1988. Then he moved to the University of Michigan, got an MS in aerospace engineering in 1990, and then moved to the University of Cambridge and was in the applied math department and ended up starting working on stratospheric dynamics and sort of changed his career away from engineering to more geophysical applications. And he did his PhD work with Michael McIntyre, who I'm sure many of you know of. Got his PhD in 1996. His first position was at St. Andrews, and after St. Andrews, he went to New York University and has been at the Courant Institute ever since, and is now a full professor there. I first met Oliver at the Woods Hole GFD Summer School. For students who aren't aware of this, it's an annual summer school held on Cape Cod where a bunch of luminaries in the GFD world get together, and then there's a small number of students who have fellowships. In my year, there was 9, and you all live together in these tiny little cottages that don't have air conditioning, and attend lectures from on extremely interesting topics that come at you at a very rapid pace. You spend a big chunk of the summer working on a project with one of the faculty there, and then scramble at the end to come up with a good presentation. And it's often a formative experience. It was a formative experience for me. And Oliver attended the GFD Summer School many years previously, and then started coming back to it. And then went on as a faculty member. And when I was a student there, and we could never figure out what year it was. I think it was 2004, maybe. He was one of the faculty there, and so that's how I got to know him. And since then, I've sort of, I've been influenced by some of his work. He wrote what I consider to be a very nice book on wave mean flow interaction, very clear. So if you want to learn more about that, I suggest you take a look at that book. Today he's going to tell us about spectral transport of internal wave energy, and he'll fill you in on why that's a subject that you might want to be interested in. Thank you very much. There we go. That should be much better.
Just, how much time do I actually have over the normally?
So we, sort of 10 to 1 is aim to start getting questions.
Okay, so thank you very much. Yes, with the change of lighting, I was a bit worried that the orange wasn't a good choice of color, but with that, that's very easy. So that's good. I want to point out 2 things here. One was a rather long list of collaborators. We've kind of been working on this in a marching formation for many years, but it's different people have contributed to aspects of this project over some time. So when Jing Zhong was a PhD student who did a lot of the work I want to talk about, Shaper Smith is a colleague in oceanography at the Courant Institute. Samuel Guri was a postdoc Courant instructorship last year, funded by the Simons Foundation, and Jalal Chattar is a colleague in the Max department. And that's the second comment I want to make. The Courant Institute is the union between the Department of Mathematics and the Department of Computer Science at NYU. And we are all housed in the Max department. So it's a little bit maybe unusual thing that for almost 20 years or something more than 20 years actually, there has been a sector for atmospheric ocean science inside the Max department. But it kind of goes back to the very unusual vision that Richard Courant, for whom all this was named, had on the unity of science, of mathematics and applications. Richard Courant was a German mathematics professor who had to flee Nazi Germany and didn't get any further than New York and built that institute there. But he had an unusually broad perspective on applied mathematics and sorts of work, original work done by the Air Force, or for the Air Force rather. There was one of the first supercomputers was housed in the building, and so it was relatively natural then to have something like atmospheric ocean science coming out of the same, being housed in the same thing. So if the name Richard Courant is not so familiar to you, then maybe if you work with computational models and your code blew up because you violated the CFL criterion, well, he's the CFL criterion, so you can blame him for that. So that was kind of one of the last things he did before he had to leave Germany. Okay, so the content of what I'm talking about is basically in 2 papers. This is the first one that just came out earlier this year in Journal of Physical Sonography. This is Beijing. So that's the main thing. So I'll give a little bit of an introduction to how we got into this, and I start by pointing out something that's well known to most of you, namely that sort of 100 years ago, you could have said that in all probability the atmosphere and the ocean should be in constant turbulent motion. Most people understood Reynolds number concepts 100 years ago, and the Reynolds numbers, of course, in the atmosphere and ocean are enormous, so they should be in turbulent motion. And of course, they are not, otherwise we wouldn't be here. The reason that these fluids are not in turbulent motion is because of the very strong effects of rotation and stratification that impose a very intricate linear wave structure onto the fluid equations that isn't there in the household kind of fluid equations or the equations you would use for flow around airplanes or something like this. So the simplest model in which you see this is something like the Businesky equations. So here just written down in their linear form, so there's a velocity and acceleration, there's a Coriolis force, there's a pressure gradient, and then in the vertical there's a buoyancy force, which changes depending on how the vertical velocity moves stuff up and down, and there's the buoyancy frequency, and the flow is incompressible. So that's the simplest model in which to do rotating stratified flow. It differs from what you would use in oceanography by that there's no salinity and there's no complicated equation of state, it's just a magnetic field that tells you whether stuff has moved up or down, and whether there's a buoyancy upwards or a buoyancy downwards because of it. So because these are just linear equations, and they're constant coefficients in the simplest case, we can just put in a plane wave solution, so wave numbers k, l, and m, k and l in the horizontal, and m in the vertical, and the frequency, and we can just collect the linear dynamics by finding the values of frequency that make this a solution to the equations. And this is elementary exercise. What's sort of page 1 on every book on GFD is that when you do this, you obtain 2 very, very different branches of the dispersion relationship that you get. 2 very, very different solutions omega for the same wave numbers k, l, and m. By the way, if you feel you want to interrupt or something, I'm very happy to be interrupted. So the first branch is the fast branch where the frequency is non-zero, and those are the internal gravity waves. So they're basically describing how the material surfaces and stratification surfaces wobble up and down, and the surfaces would be flat at rest, and if they disturb, there is some kind of energy cost associated with that, and they kind of try to restore themselves, and they overshoot and they oscillate. And the famous dispersion relationship is here. The frequency of the waves depends on both n squared and f squared in such a way that actually only the angle that the wave number vector makes with the vertical actually affects the frequency. The frequency is between f and m. And what do these waves are fast. I mean, there can be minutes in the atmosphere, which is very, very fast, hours in the ocean, which is also very, very fast. And what do they look like? Well, it's a long time ago, Carol Bühler did a thesis with us, and she worked on internal tides, which are also internal waves. And so she had this little visualization of internal tide created by flow rubbing back and forth over a little hill in the seafloor, and she put a little fish in there to illustrate the motion. And it's a dead fish, right? It's not moving itself, it's just moved by the water. So apologies. I know many people here study stuff that's actually alive in the ocean. So this one is not, but it illustrates what's happening in terms of these waves and the kind of peculiar and intricate patterns. These waves were most infamous because they were the reason that Louis Fry Richardson forecast in 1926 failed. Louis Fry Richardson was a Scottish mathematician who was very stubborn, and he said we can actually predict weather not by staring at the clouds, but by the process of numerical computation. So he, by hand, tried to forecast the weather somewhere in Britain, and it completely failed because the system was entirely unstable because of these very fast waves, and because he couldn't control the time step. Because when you have to take a time step of 6 hours in his hand calculation. But because he was a genius, he didn't just hide this work, he wrote a book about it, which became very, very influential. But it's these fast oscillations that were the reasons why his forecast failed. So one thing that's important for what comes later is that if you use wave theory based on a dispersion relationship, one thing you can compute is the Brook velocity, the speed with which waves propagate, by just being the derivative of this dispersion relationship with respect to the various components of the wave number vector. And if you do this, because the frequency doesn't change if you make the wave number vector longer, but not change its direction, that implies then that the group velocity, if you do the same operation, goes down if you make the wave number vector larger. In other words, these waves slow down when you make them smaller somehow. If you reduce the wavelengths of an internal wave, its speed of propagation will go down. And that's an important fact for what will happen. We'll see later. Okay, so that's the internal wave branch that sunk. So that's this peculiarity I just talked about. So that's the reason why this forecast failed and why they're a big nuisance. And so what about the other branch? Well, the other branch is the slow branch, which in the linear theory just has zero frequency. So omega is actually zero, and you have a flow that has no vertical motion, and the pressure gradient balances both the Coriolis force in the horizontal and also the buoyancy force in the vertical. So these are called the balanced flows, and they are described by a stream function in the usual way, or the Geostrophic stream function. And they are the reason why this counterintuitive result is true, that you know from everyday experience that air or water should move from high pressure to low pressure, and yet when you look at the weather map, strangely the flow seems to be going along contours of constant pressure rather than moving across from high to low pressure, and that's because for this mode it moves along lines of constant pressure. So it was Jules Charney's great discovery in 1947 over a number of years and steps that one could make a nonlinear dynamical system out of this balanced mode, and it is that nonlinear dynamical system that was basically the foundation for the first truly successful weather forecasting operations, because they were now devoid of all these fast motions that kind of tripped Lewis, Fry, and Richardson's ability to forecast. So with that, great enthusiasm ensued for the balanced mode and for the slow evolution, throwing away all these waves. So much so that there's a beautiful letter here from Jules Charney, February 1947, so day zero, ground zero for the creation of QG theory, in which she writes, and let me read this out to this friend: in the terminology which you graciously ascribe to me, we might say that the atmosphere is a musical instrument on which one can play many tunes. High notes are sound waves, low notes are long inertial waves, and nature is a musician more of the Beethoven than of the Chopin type. He much prefers to low notes and only occasionally plays arpeggios in the treble, and then only with a light hand. The oceans and the continents are the elephants in Saint-Saëns' animal suite, marching in a slow, cumbrous rhythm, one step every day or so. Of course, there are overtones, sound waves, billow clouds, gravity waves, inertial oscillations, etc. But those are unimportant, and I heard only at NYU and MIT. So this beautiful quotation. Internal wave research kind of took a backseat. Also, by the 60s, it was discovered, or it became clear in the atmosphere that internal waves contributed significantly to the angular momentum transport, and you needed to do something with them. In the ocean, really not much happened for a while, except there was sort of a renaissance some 50 years later with this kind of this plot that launched 1,000 ships, which is the direct measurements by the Woods Hole of ocean turbulence over topography. And all you need to, if you haven't seen this plot before, all you need to realize here that the turbulence intensity is measured on a logarithmic scale, meaning that the dark purple is very, very low turbulence, and the yellow or red color is much, much more turbulence. And where the topography is more or less smooth, there is sort of low turbulence, and where it's jagged, the turbulence is greatly enhanced. That was an indication that the turbulent mixing is highly correlated with the topography there, and therefore presumably with internal waves radiating away from this topography. And that was important for the vertical mixing, and therefore, in the end, for the long-term overturning circulation in the deep ocean. So that kind of made a big gravity wave research comeback in oceanography. And so one of the main questions really is, how can you understand the fact that when you go out in the ocean and you put an instrument down and you measure the frequency spectrum of the waves, you will find that there's invariably a broad spectrum. I mean, don't worry about all these measurements, just a randomly pulled paper from the last few years, 2020, showing measurements of frequency spectra somewhere in the top 400 meters of the ocean, and under various conditions. And all I want to point out is that this is a frequency spectrum, the sort of F, the Coriolis frequency somewhere around here. The tidal peaks are marked, and you can sort of see little blips where the tidal peaks are, but there's a broad spectrum all the way down to either the Nyquist frequency associated with the instrument or the buoyancy frequency when the waves stop. So it's a very broadband spectrum, that has been observed for a long time, and yet the known sources are extremely monochromatic. There's the various tidal ingredients, which by their very nature are monochromatic. There's the direct input by wind, which it's not the time dependence of the wind that plays any role, but it's the aspect ratio of the response in the upper ocean that's important, and that basically means that it's extremely low frequency near inertial waves can only be generated by this process. So there's the question, how does the frequency spectrum get filled in, given that all the sources that we know of are practically monochromatic? And so in the 70s and in the 80s, the basic thing that people concentrated on was, well, if a bunch of waves, linear waves, but they're not really linear waves, they live in a nonlinear reality, so they will not stay linear forever, they will interact with each other. Therefore, by wave-wave interaction, you can change and modulate frequencies, and maybe that's the dominant mechanism to fill in the spectrum. That was kind of the conventional view in the 70s and 80s, and that is still undoubtedly an important part of the dynamics. We are also having some research project associated with that. But it also has become maybe clear that the interaction between these waves and the actual balanced flow, kind of large-scale currents, are important. And here's a numerical experiment from 2017, and there's a recent, the same authors produced an update of this more realistically just now. And sorry, this is, don't want to explain in detail what they did, but this model of the numerical model of the upper ocean, and they forced this model by wind stresses, and they did a very clever thing. They either only forced it with very low frequency wind patterns, or they forced it with only high frequency wind patterns, or they forced it with a combined low frequency and high frequency wind patterns. And the idea was that if you do the low frequency wind pattern, so the wind was almost steady, then you would predominantly excite the vortical mode, the balanced flow. You can see these vortices here, and you would create very few internal waves, if any. And indeed, you can kind of see this in the spectra are all very, very steep here, and there isn't any particular. This, I think, is the Corona's frequency. There's a little bit of a kick in there, but there's no real spectrum developing afterwards. And if you do this with, so as low frequency, you have sort of low waves. With high frequency, you get a bunch of waves, but not really a spectrum. And then, but if you combine them both, you suddenly get both the vortical spectrum and the wave spectrum kicking in and looking very realistic. And there's a switch on here at the Corona's frequency and the broad spectrum behind it. So that was sort of the suggestion. In order to have this broadening of the frequency, that maybe it's not the waves on there by themselves, it is the interaction of the waves with the flow that allows you to broaden this frequency spectrum. And that's kind of spawned a bunch of research. And here's a very nice theory, not by us, but by Jacques Van Nest at Edinburgh and his collaborators, about how there's inertial gravity waves be changed by geostrophic turbulence, and how this can be looked at as a certain kind of diffusion process in wave number space. I don't want to belabor this. It's just they sort of start with the conservation law for wave energy or wave action. And there's sort of a group velocity term moving stuff around, and then there's a refraction term that can change the wave numbers following the waves. And under certain considerations, when the mean flow is very weak, which it is in the ocean, then this kind of advection and refraction by the mean flow can be approximated as a diffusion process by a theory that is well known, and adapting this theory that gives some expression for this diffusivity. And the beauty of the result is that it's a very simple outcome. I just want to show you the picture. In three-dimensional space, the frequency of internal waves is constant on cones. And basically, by this process, the waves can spread out on this cone, so they can change their wave number, but they don't change the actual frequency. So they kind of do spread around. There's some kind of strange diffusion in wave number space, but they don't change their frequency. So we kind of termed that Las Vegas dynamics. So what happens on the constant frequency cone stays on the constant frequency cone. They can move around there, but they can never change their frequency. So if you want to remember what that is, this is the Las Vegas dynamics. And crucially, this does not explain any frequency broadening. The waves, the sources, they're monochromatic in frequency to begin with, then the response of the fluid would remain monochromatic. In frequency, it would just change in wave number. So it's a very nice theory. It's undoubtedly correct, but it doesn't seem to be describing this frequency broadening. So This is where Wenjing's project comes in, where she, instead of trying to use an equation which is sort of a simplification of the actual refraction by the mean flow, she just studied directly the refraction by the mean flow by looking at kind of wave packets propagating through the ocean. So they have some location x, they have some wave number k, indicated by this nice little purple arrow, and they're kind of meandering through the ocean, experiencing the mean flow along the way, and then we can work out what happens to them. So the theory how that works is all very, very, very standard wave theory, geometric wave theory, that you have some frequency function that is the sum of some Doppler shifting term plus the intrinsic frequency that we saw earlier, the one that depends on n and f. And then you have the standard kind of ray tracing equation that the wave packet moves with the group velocity of the waves, which will now include the mean flow as well. And then the wave number vector will change by the spatial gradient of this omega function. So it's all fairly straightforward, except that the application is a bit complicated because you have a three-dimensional problem on your hands. In the simplest case, you can sort of see that the refraction of the ith component of the wave number vector has to do with the derivatives of the mean flow in that direction. So if the mean flow doesn't change in the x direction, for instance, then the x component of the k vector would remain constant, but in general in the ocean it changes all directions, so nothing stays constant. Okay. And then this slide, unfortunately, is from some other thing where this was done with shallow water, so ignore all this. Just to say that in the end, you can use Bretherton and Garrett's result from 1968, that the wave action, the ratio between the wave energy and its intrinsic frequency is a conserved quantity that you can compute afterwards, after you found where the waves are going. Okay, so with that, we are ready to shoot some rays through the three-dimensional internal wave ocean. So these are the actual equations encountered by the wave number components in 3D. And because in the ocean the balanced flow only has horizontal velocity components, the three-dimensional wave number vector, its evolution splits into two parts. One for just the horizontal components, and then one for the vertical component that you can kind of solve in a sequence. So it's really this 2x2 system, and then this one follows by whatever K and L decide to do with the rest of the derivatives, which makes things a lot easier. Oh yes, so this should have been there already. So the mean flow has no vertical component, which is why we have this split into a 2x2 system. Okay, so as I said, and basically you can kind of, there's an analogy between the evolution of these wave packets and the erection of a passive tracer. The wave number vector can be compressed or strengthened in the way that passive advection would bring contour lines of the passive tracer closer together. But when that happens, then remember this peculiarity, the wave will slow down. Okay, so what Wenjing then did is she set up a kind of artificial ocean where you just have lots of kind of modes for a stream function that follows a suitable power law that's sort of realistic for submesoscale turbulence. And then she was ray tracing the rays through this flow, and in the first instance, the flow was just completely steady, just the waves were unsteady. And of course, this being the simplest possible version, she did it first in a triplet periodic domain, but she also put walls in for the ocean. It didn't really make any difference to this. And then we launched rays from random locations in random directions, but they all initially had the same frequency. So we wanted to really start with monochromatic wave sources and see what happens to them. So do the waves come off the constant frequency cone, or do they stay pinned to their original frequency as compatible with that diffusion theory that I mentioned earlier? And basically, this is the main result. Here's a frequency spectrum normalized by f. So everything starts at omega is equal to f, and then goes up to omega is equal to n, I think over here. And this is the original frequency that the waves all had. So it has one, whatever it was, 2 or 3 versions, multipliers of f. And then that's at the initial time, and then as times go on, it rapidly spread into this kind of broadband spectrum. So the red line is the earliest one, and has this shape, and then it quickly becomes something that actually seems to approach an equilibrium shape. So something that by itself reaches a kind of steady state, doesn't change very much anymore, as these waves are refracted by the mean flow.
Sorry.
Yes, please.
Does that the spectrum, does it depend on the choice of your emission frequency?
No, it does not. So that's a very good question. Basically, it depends. I will talk about that more, but just because you asked right now, it depends on the nature of the mean flow. But anyway, if you could see that here or there, it will all become the same spectrum. So it forgets where it comes from, just gets squeezed out into this thing. Yes, please.
I have a question. So, if we assume scale separation, then ray tracing tells us that the frequency doesn't change unless the mean flow has time variation. So, I think that's probably violated because the scale of the waves and the mean flow is not separated, or.
So thank you, that's a very good point. So I think what you're referring to is the ray tracing equations, if the mean flow is steady and the absolute frequency is precisely conserved. Yes, and if it starts at whatever number, it will stay at that number forever. This is true in these simulations. So what's changing here is the intrinsic frequency.
Oh, okay, the intrinsic frequency.
So in the diffusion theory, basically the Doppler shifting term, which is the difference between these two frequencies, is treated to be small at all times. Basically, then the first one, the conservation of absolute frequency, will imply that the intrinsic frequency can't do very much. So another way of looking at these results is given that the intrinsic frequency greatly departs from its original values, that means the Doppler shifting term does not remain small, even though it started small. That's the main thing. But yeah, thank you. So these waves do not stay on the frequency cone because the dynamics is very much not Las Vegas. It doesn't stay here, it gets spread out everywhere. So the completely called the New York dynamics, if you can make it at one frequency, you can make it then at all frequencies. So that's these waves promiscuously kind of change and rub themselves out over all possible frequencies accessible to the system. And so that was a big surprise that this happened. So the first thing was, obviously, this was an artificial flow. It was just a random Fourier series. So Schaefer had plenty of quasi-geostrophic turbulence simulations. So what we did is, we took one of his simulations, as you see, so this looks more realistically, sort of vortices and patches and filaments. And we took that flow and put lots of rays through them. And then we took the same flow and scrambled all the Fourier phases, so you get porridge. It has the same power spectrum, but they have different phases. And then we sent the rays through there and wondered whether this will make a great difference to their effective dynamics. And the answer is, surprisingly, I think it does make absolutely no difference, basically. So you can see there's the blue here is the QG flow, and then the red one is the synthetic flow, just with the faces scrambled to these two pictures, and the spectrum is essentially the same, except at the very end here, close to N. And that's, I mean, I still find that surprising, but one thing, I guess, what one needs to bear in mind with these kind of pictures, if you keep the power spectrum the same, and you scramble the phases, statistically, these two flows still have the same correlation structure. So the correlation hasn't actually changed. So the 2 points are still as correlated in terms of their flows as before, even though they scramble the phases. That really is a surprising mathematical fact, that the correlation in a random field is only a function of the power spectrum. It's the Fourier transform of the power spectrum, and has nothing to do with the phases. And I think somehow it seems that it's only the correlation structure of the flow that actually matters, and that is in fact the same between these two pictures, even though you don't want to believe that. So it seemed that it wasn't important to put a realistic flow in there. All you needed was a power spectrum that matched the situation that you had. So how is that possible? So the results suggested the emergence of universal spectrum related to the correlation statistics of the mean flow, those being the ones that are unchanged by scrambling things out. So what's going on? So here's our first attempt of trying to explain this is sort of a theory based on this wave capturing mechanism that proposed some time ago for internal waves that get sufficiently stretched so that their wavelengths become so small that their speed just becomes so reduced that they basically just get passively advected by the flow afterwards, which is this capturing mechanism. They start moving around and then they get strained and slow down, and then they just can move this little flow and they kind of have no life of their own anymore. So describe that as the same equations as before, and you have these 3 opportunities, these 3 possible pictures here, that you either have some kind of straining flow in this parabolic limiting case, or you have sort of elliptic flow where there's not much systematic straining going on. The criterion that tells you for the local flow what's going on is this parameter d, which of course is the Okubo-Weiss parameter. And there are three things that are remarkable about this. First remarkable thing is that this parameter does not depend on the orientation of your horizontal coordinate system. So if you rotate your coordinate system by 20 degrees, you get the same number d for the same flow, even though all the ingredients, of course, of this object, they all change, but they change in such a magic way that this particular combination stays the same. So it's a proper scalar. It doesn't depend on the coordinate system, although it looks like this. The second remarkable fact is that it's called Okubo and Weiss, even though Okubo's paper was in 1970 and Weiss's paper was in 1991. And I looked at them once, I can't quite. It wasn't so clear to me what the necessary contribution here was that made it Okubo-Weiss, but I stuck with that terminology. And the third one is that this was originally conceived, of course, for sort of two-dimensional flows, but it applies here. We call the aforementioned split, that this evolution of the wave numbers first is in the 2D plane, and then the third direction sort of slaved to what happens there before. So this kind of two-dimensional picture actually applies very well. Okay, so when you do this, then what you can now say is if you have a given strain matrix here, then this mean flow refraction that will rotate the wave number vector in the direction of some kind of growing mode of this matrix, and will stretch it in that direction. That will reduce its group velocity, and it will also select a particular frequency just by the eigenvectors of this matrix together than what happens there. Of course, the whole thing is really a three-dimensional matrix. You can look at their eigenvalues, and you can see that every location, if it acted indefinitely on a wave number, on a wave vector, it will rotate it into a very specific direction in 3D. There will be a specific frequency then associated with that, and that will be the target frequency coming from that location. So what Wenjing then did is she did some kind of census where she just sampled the mean flow gradient at all points in the domain, and she took all the points in the domain where the flow had kind of straining lines like this, and then for each of these points she computed the kind of target direction, associated target frequency, and said that's what should be the case. And when you do this kind of eigenvector analysis, this is the outcome. So you have from the QG flow, you have the ray tracing result here in this kind of awkward color, and then the synthetic flow, you have the ray tracing result in this dark purple, and they're here. And then the theory based on this eigenvector analysis is the two lines on top, and basically it's a reasonably good fit. Some kind of mismatch in amplitudes between them, but the basic trend is very well captured by this eigenvector analysis of this random flow field. So that was very encouraging. Eigenvector theory based on grid point census really clearly works, but one can actually make the theory simpler still and get a meaningful answer, which is based on this paper from atmospheric tracer advection from some time ago, 1997, Peter Haynes and in Cambridge, and Jerome Anglade, and I know about this because I was still in Cambridge when this happened. My PhD, and he was a French exchange student, and they looked at a model for passive tracer advection in the stratosphere, which again is of course dominated by horizontal winds, and they looked at some kind of trajectory stochastic model where the flow was just purely strain, there was no vorticity, and they modeled this with independent random processes, and what they found is that they could get a closed equation for the typical aspect ratio of these stretched and advected filaments in the stratosphere. So if the vertical wave number is n, then the ratio between the size of the vertical wave number and the size of the horizontal wave number, call that capital X, they could find an equation for it, and in fact they could solve it in certain limited cases. And that included the case of where the flow was very slowly time dependent, in which case they got this simple formula, where the probability distribution of this random variable X's aspect ratio is a particular formula like this, where alpha is a parameter that measures the aspect ratio on average. Alpha is very large. And it turns out, well, we can just take this theory, which in its key ingredients uses the same equations, and adapt it to the case at hand. So this is the results from their theory, and all we added was saying, well, the frequency of internal waves, here it is, it only depends on the aspect ratio. So the frequency can be written as a function of the aspect ratio and vice versa, and therefore we can translate this probability distribution for the aspect ratio to a probability distribution for the frequency by using the normal kind of calculus for doing this, and then we get an explicit answer longish formula for what that frequency spectrum should look like as a function only now of omega, and alpha, which is the only thing that matters from the mean flow, which is the kind of aspect ratio parameter from it's a kind of measuring the aspect ratio. And this is the result. And again, there are too many lines here, but let me just say it works extremely well. So we have a bunch of lines here. And I think the strain shear model is the dash line, not the dot line, or not the solid line. But if you look at any case, the dot, the solid and the dash dot, they're all very close to it. It works very well. So we don't even need to do this complicated eigenvalue census, eigenvector census. It's a simple kind of one-dimensional probability distribution. Works for basically all the cases that we get. I should say that this wonderful theory does not predict the Garrett-Monk frequency spectrum, which is omega to the -2. It predicts stubbornly omega to the -1. It would predict omega to the -2 if we forgot Brotherton and Garrett's result that it's not wave energy that's conserved, but wave action, because that gives you exactly the factor of 1 over omega that you would need to turn this into omega to the -2. That would, of course, be spot on what the GMs, the Garrett-Monk spectrum, is expecting, but the theory predicts a slower rate of decay, at least in this version. Okay, so so how does this now relate to the diffusion theory that I mentioned earlier? Well, basically, the diffusion theory did this. This was the Las Vegas dynamics. Everything stays on the cone there, and the new theory doesn't do this. And the way these two things are compatible is that this theory definitely applies, but it applies only at the very initial phases of the motion. So here are some plots. The time has been rescaled by the Rossby number squared. You can kind of see that the diffusion theory is kind of this shallow bit of the lines. And then when the Rossby number squared times the time becomes not so small anymore, then they all take off. So basically, the diffusive dynamics is some kind of precursor to this dynamics that later takes over, where the ratio of the mean flow to the group velocity, it may start small, but then it doesn't have to stay small. It can become large, and then the wave dynamics completely changes. Okay, so that's here the later tapes. The York dynamics takes over. One frequency can spread to all possible intrinsic frequencies. Okay, so then there's the second piece of work. This was Samuel Bory and Jalal Shattar, which is really was trying to dig into some of the theoretical aspects of this by looking at this kind of fast, slow transition. The wave may start fast compared to mean flow, and then it transitions to being a wave that's slow compared to the mean flow, and whether that's something one can study sort of on an idealized level. So it's this paper that came out just now is about physical review E, and basically it's the same equations as before. So it's a weak mean flow, and there's a dispersion relationship here, and the flow starts with such that the group velocity is large compared to the mean flow. So this is a small parameter, but it's a two-dimensional problem. So it's just a toy model, and the dispersion relationship is just some power law alpha. So it's k to the alpha. So if alpha is something like 1, then it would be like shallow water. If alpha is a half, it would be like surface waves, something like this. But the point is that the group velocity then becomes proportional to k to the alpha -1. So whenever alpha is less than 1, you have the same effect as you have for internal waves, that an increase in the wave number, therefore shortening of the waves, goes together with a slowing down of the waves. But for alpha larger than 1, or 1, you don't have this effect. So what Samuel did, he first looked at kind of steady flows, and basically get depending on the value of alpha, you get some very different results. So here's a value of alpha that is slightly more than acoustic or shallow water. The waves are happily flippering through this domain, and they don't care too much about the kind of mean flow pattern that you see here. It's a stream function plotted. And then their wave number vector, they kind of more or less stay confined to a ring of constant frequency. And indeed their frequency kind of bubbles around, but there's no net trap. And that picture is very different when alpha is something like the surface wave case, where the waves flicker around, but then they encounter a strong vortex, and then they sort of get trapped by this vortex and stay there forever. And the the frequency can then change by a large amount. So what Samuel explored was whether this is something that one can quantify and understand, so there's some kind of matching between waves then predominantly assembling inside vortices. So it's just a kind of empirical joint PDF between the location of the waves, which are all these red dots, and the vorticity, if you like, of the vortices, and the alpha equals 1.2 case. There's no correlation really establishes itself. The waves are just as likely to be found inside or outside of vortices, they don't care. But when you have this alpha equals a half case, then they start with no correlation, and then they develop a kind of sizable correlation between their location and being in vortices that is very, very strong. And I'm not sure what this psychologically looking plot is as a way of illustrating this local PDF of local values of this. I think all it was meant to show is that there's nothing much to be seen up here, and there's a bit more blobbiness down here, that these strong vortices seem to be close to a lot of vortices, a lot of waves, which is of course true. And the most exciting thing is that what Sam found is that you can make a diagram like this, collate lots of results. Here's the parameter alpha. So alpha above 1 is uninteresting because those waves don't experience any transition. But for values below alpha, what this plot indicates, all this kind of blood red here, is waves that have become slow and become trapped in vortices, but they may have started being fast. And there's a boundary here that if you start fast enough for all these values of alpha, there's some regime where the Las Vegas dynamics persists. You flipper around forever and never transition into this slow regime. In some cases, you can actually compute the value for this boundary. But that only works if you're extremely slow to begin with in the mean flow. And this was all done for a steady mean flow, which of course is very special. So the final thing that Samuel then did was he actually let the flow become time evolving. It's not really fluid dynamically evolving, it's just a random evolution of the Fourier coefficients, allowing them to change their phases slowly. But that does mean that this picture here is a kind of conceptual picture. This is what the steady situation was, where there was this thresholding behavior that the waves are fast enough that they will stay fast forever. And then as you make the flow slowly more time dependent, as a parameter that measures this, then this boundary basically disappears. And after some time dependence, you have a flow where all the waves transition, all the waves that have alpha less than 1 transition to the slow regime after sufficient time has elapsed. So this kind of this blood red stuff now covers everything. There's no escape. There's no way that you can keep your fastness. So the New York dynamics, if you like, is the unique attractor for this kind of dynamical system. So with that, let me make some concluding comments here. So what we found is that the internal waves in this kind of sub-mesoscale ocean dynamics, they very, very easily change their intrinsic frequency when refracted by the mean flow. So just any amount of ray tracing, anything you do, it's a very strong effect. It's not inevitable. That's even though there is a diffusive regime that precedes this, but it's really just a transient regime that kind of afterwards becomes this. So it creates a spontaneously broadband spectrum, which is therefore seems to be a good candidate for playing a role in this in the observed broadening of the spectrum in the ocean. The 2D model, which is just a theoretical toy study, it shows that it's possible to have regimes where this diffusive regime persists for a long time or even forever, but that only holds for the extremely artificial case where the flow is absolutely steady. Once the flow is not steady anymore, then this kind of diffusive regime seems to always go away and be replaced by the regime where the waves just say, dang it, I can do whatever I want now. I will escape this constraint and go to whatever frequency I choose. The main caveat, and that's really that where we are now, is that all these experiments and all the theories were really for the initial guiding probability. So start with the wave at a certain frequency, let it go, and you monitor how it's spread out over many more frequencies afterwards. That's not what you actually observe, of course. When you measure something in the ocean, you get some kind of force dissipative equilibrium where there are many waves constantly being generated, many waves constantly being dissipated, and many waves undergoing transitions all the time. So you really need to apply apply the same thing for the force dissipative part of this, so basically transform, instead of looking at the initial value problem, we're looking at trying to see some kind of force dissipative equilibrium where we constantly put in waves and also dissipate them at very small scales. And we would have probably already done this, except when Jing did very good work on this and other things. She was so excited by this that she immediately went into banking after her PhD finished. So now in postdoc, another student were going to work on this, but I still have some time to ramp up and reach the same level of fluency again. But that's where we are now. We do believe that what we found there is robust and is going to be a part of the story. But the fact that it's all the initial value problem does make it a little bit hard. So is that
Questions? Go with Edmund.
Yeah, so does all that depend on characteristics of the mean flow? For example, if the mean flow is kind of very smooth, or is it, because you're talking about straining and stuff, so that assumes that you have some eddies and stuff in there. So what controls that, or what's the characteristic of mean flow then?
Yeah, that's a very good question. So originally we thought all kinds of things to do with the mean flow will control this, which is why we tried this QT simulation where there were actual coherent vortices, and we just scrambled the phases and the waves seem to be doing just the same. So the presence of coherent structures of vortices seems to be very little impact to the actual dynamics as felt by these waves, as long as they, the kind of these experiments, which is this peculiar thing that it's power spectrum more than anything that determines it. So that we didn't show this, but there were different simulations using different power spectra or something, and the borders all showed the same thing, all the details differ. If in the final bit of theory for the actual internal waves was this application of this theory from the stratospheric wave spectra, and that theory in the end has a single parameter that determines the spectrum. There's this one parameter alpha that knocks around there, and so basically the entirety of what your flow is doing boils down. There's one parameter alpha you can compute basically from that flow one way or the other, and that all the flows that have that same parameter, they will produce the same spectrum. This whole universe. So it is surprisingly little that seems to actually go into giving you this shape of this spectrum, which is a very, very spontaneous, very robust thing that seems to show up all the time. It's very, very little. But you can take an extreme example, like some of these studies, sort of isolated ways, lots of people have looked at like just a barotropic flow or barotropic and one barotropic flow. It's a very, very restricted vertical structure. Then you do get completely different results. And it has to have lots of poles in it. It has to be multi-scale, and it has to have aspect ratios that the waves can tap into. But outside these extreme examples of effectively really reducing the dimensionality of the flow, it seemed surprisingly insensitive to anything. In particular, I mean, the fact whether or not you have coherent vortices for the broadband evolution of the spectra seem to be very, very, very low importance, which is surprising for what I think coherent structures do with straining and so on.
So a related question. If you make the mean flow time dependent but keep the correlation feature the same, do you expect the same broadening spectrum, like same shape?
What do you mean by keeping the correlation the same?
You showed the two view graphs. One is scrambled, another is like beta organized.
Right.
So presumably, if you say the correlation structures right now they are the same, even though it's scrambled. Presumably, if the correlation structure is different, the final spectrum would be different.
I think so. So let me. I tell you one thing that we did, and maybe this is closer to what you're asking. So we tried to use time-dependent QG turbulence relation. And that brought in a problem that I think touches on what you were saying, that if you just take a freely evolving QG turbulence relation, it will not be time invariant. The statistics and the correlation structure will change in time. The modules will get bigger and so on. So that's not stationary in time process because the character of the mean flow changes. In order to make that something that's stationary, in a sense, you need to force it to dissipate and do some kind of one of these simulations. But if you do that, then the correlation structure is the same all the time. So basically, our impression from trying various things was that as long as the correlation structure, i.e. the power spectrum, stays the same, whether you do this with synthetic evolution, using the phases of the Fourier transforms, or whether you actually evolve it with a fluid dynamical integrated force dissipating, that seems to give the same answer. So there was no memory effect, basically, that we could detect. It was really only the kind of instantaneous spatial correlations that flow with a relevant thing. And whether you maintain those by random Fourier series or whether you actually get those Fouriers all this involved by proper fluid dynamical integrated it's basically, there seems to be no memory that's relevant for the three-dimensional. That's what it wants to do, based on the instantaneous propagation. It's really, if you go back to the original writings about the Okubo parameter and all this, it's really, the wave is kind of propagating through the universe. As it does that, it encounters various velocity gradients along its way. And it's really the kind of sequencing of these velocity gradients along the way of a wave packet that is the only statistics that matter. So whether the wave packet encounters a new velocity gradient because it moved a little bit, or whether it encounters a new velocity gradient because the flow changed a little bit, it seems to make no further difference. It's just kind of lots of statistics of successive experiences along this wave path that governs it.
So you would expect this to apply for the atmosphere as well, because you have the mean flow and then you have lots of internal.
So that's a very interesting question always, to what extent can you kind of have a technology transfer from one to the other? My experience with atmospheric internal waves is that mathematically they're of course very similar at first sight, but the details do matter. Like in the ocean, it's very easy to think about waves to be extremely long-lived. They can hit the top and they can reflect it down, they can spend a lot of time in the oceans following them. In the atmosphere, almost always live for a day or two. It's a single shot. They go up and then the density increases, and they break and they break off. So the scope for actually forming something that looks like the universal spectrum is much, much more difficult. In fact, I think it was one of the few attempts to have a theoretical technology transfer from oceanography to atmospheric science, and not the other way around. When people sort of said, oh, let's do something like finding the Garrett-Martin spectrum in the atmosphere, just Van or something spectrum for a while. But basically that has died down because there is no, it's not a, wherever you measure you get different answers to it, so whether you probably or not and so on. So there isn't really this kind of long reservoir that everything's on top of each other and you kind of adjust to this. So I think I don't think you'll be able to find any of that in the atmosphere because of they just only live a day or two of it. And propagation is almost entirely vertically. There are a few reflected ones, but it's mostly a one-shot thing.
So this is probably a dumb question. Going back to the toy your student made, when I was looking at it, it looked to me like more of almost like the surface gravity wave, the way it was moving. But that was supposed to be reinforced by internal waves. Can you explain that?
So, you mean something like this?
No. The little toy with the little fish. Because the
fish.
So I'm looking, why does that particle, why should that particle move like the way it was moving?
Why is the dead fish moving the way it moves?
Side by side rather than up and down.
This one?
Yeah. Why is it moving?
Yeah, so there is a remote possibility that Karin only plotted the horizontal motion of the fish. But I think the vertical excursions, this is on a fairly reasonable scale. I mean, the typical thing, this is internal tide. So the idea is you have the barotropic tide that moves everything like 100 meters back and forth all the time.
Right.
So this is sort of the horizontal scale here is like 100 meters wobbling back and forth, and then there's some kind of topography structure underneath that both the flow is to get out of the way, and that sets up this kind of wave field. Having said that, the horizontal excursions of particles are much larger than the vertical excursions. So even if Caroline plotted the vertical displacement here as well, it is probably tiny compared to the horizontal one, which is simply a reflection of the frequency of these tides. These are modest multiples of f, and they have fairly shallow aspect ratio. The motion is almost entirely horizontal, so it looks like this. You kind of see also the way this works with these. The waves tend to come off in particular directions associated with the frequency of oscillation. So like these kind of wave beams that people studied a lot. And the way this is drawn, that fish finds itself outside those beams. So in some sense, it only sees the kind of sloshing back and forth. Whereas if you have put the fish in here, you can see all these lines are material lines. So here there are very stronger vertical motion, just where the fish is vertical fish. There's nothing happening. So that's the answer. But as I said, this is a particular example where the internal wave gives a direct response to this barotropic tide just wobbling back and forth and creating waves here. So there's no mean flow, nothing is here. There's also no miracle or controversy about where the frequencies come from. People are very happy to find these spectral peaks. They can identify them in the spectrum. Oh, this is the M2. And if they can follow them, they can write a grant and go to Hawaii to study that more carefully, how the tides are coming off the Hawaiian, because that's really important. And so that thing, there's the inertial peak itself from the wind forcing directly at these M2 or other tidal peaks. Those are the bits of the spectrum that are really understood. There is this bit that's a bit just at F, and there are these tidal peaks. It's all the stuff in between, but has no direct sources. That's harder to pick up. Thanks.
Quick question, and then we should go to lunch.
The fact that your spectrum doesn't fit the Garrett monk, it's -1 instead of -2. Is that a factor of the fact that you don't have dissipation? If you have dissipation, suck it down the high frequency, would it be closer to -2?
So that's because of the lure of the banking industry. We don't know that yet because Jake disappeared. But that's exactly that. I mean, there's absolutely no reason to think that the spectrum you get from an initial value problem should be the same that you would get if you added forcing and dissipation. Indeed, there can be effects, can be turnover or go down to something else. So we don't know. The oceanography standard of how to put dissipation into a turtleneck spectrum is not very highly developed. Basically, the Garrett-Monk spectrum, you just cut it off when the vertical wavelength gets to 10 meters or something, and say, okay, at that point the waves dissipate. That's not the most sophisticated way of doing it, but that's probably, we can do this in these simulations as we have the vertical wave number, the vertical wavelengths evolved along the ray, so you can kill the ray at that time, and then you need to put fresh ones in. So it's clear how to do it, but it hasn't. These simulations are not super sophisticated. They are, however, quite demanding, and one thing we found is that actually to have accuracy on these rays, like to get the fact that the absolute frequency should be conserved for long integrations, which these are, is actually very hard. So one thing that the student is doing just now is we got some advice from numerical analysts that, of course, these people have developed very sophisticated methods to integrate Hamiltonian systems that are kind of tuned into the geometric structure and do this much better than just using a Riemann-Kutter scheme or something. However, those schemes tend to be implicit and more laborious to code up, but we are doing this now, and the results are very promising that the behaves much better. So although these are very straightforward simulations, they were actually extremely costly, and they would run on the supercomputer and so on, because a lot of rays, and maintaining the accuracy was surprisingly difficult. The time steps had to be tiny and stuff. It always felt like we were doing something stupid, but there wasn't an obvious way of improving it except throwing more effort at it. So we couldn't just do it in the afternoon before she left for her banking job. But we hope that we are on track to see this.
All right, well, thanks very much, Oliver.
Thank you.